Hello, everyone. Thank you very much for joining us today. We are coming to you from Tucson, Arizona, as usual, and we are looking forward to your questions. I'm going to hand the session off to Professor Impey, and we'll start grabbing questions from email and from the live chat. So if you have a question, feel free to put those in there, and I will grab those as they come by.
Okay, welcome everyone. Good to have everyone on board. Large number. We're really getting our numbers up here. We've been close to 200 a couple of times, which is amazing. If you hear a little background noise, I'm afraid that's unavoidable. I'm at Steward Observatory, and they're working on the building under a fixed price contract, under a tight deadline, and they're in the corridors on both sides of me. So we'll just have to work with that. Ready for your questions.
Thank you very much. Okay, the very first question is from an email. The person's name is Han, and the question is, why do elliptical galaxies mostly contain old stars, and how do they form?
So the galaxy morphology is a clue to history, formation history, and nature of the stars. The basic subdivision of galaxies is spirals and ellipticals. We kind of know a lot about spiral galaxies because we live in one, so we have a ringside seat for all the details of at least one spiral galaxy. Elliptical galaxies in general are older, more massive, and redder than spiral galaxies. And all of those things have a consequence in their formation. They also have a more symmetric shape, being sort of ellipsoids in 3 dimensions. The age and the redness, those things are associated because it means that these galaxies formed fairly early in the history of the universe. So as the universe ages, their stars and stellar populations have aged and reddened, as will happen to all stars, because the blue ones are the young ones that die first, leaving behind white dwarfs, or neutron stars or black holes. And in the end, all you're left with is the red stars, the lower mass ones, and some evolved red stars. So that's why ellipticals are red. The early formation also is part of why they're the shape they are. So elliptical galaxies, we think, formed from the collapse of nearly spherical gas clouds that had some rotation, and they preserved that nearly spherical shape by becoming 3-dimensional ellipsoids. Most of the gas was consumed in making the stars, and so what's left is a stellar system with very little gas, and that's characteristic of elliptical galaxies. However, they are not evolved in the history of the universe, because we also have a universe where structure was built up hierarchically, smaller things merging to form bigger things. And something we see as a giant elliptical galaxy in the nearby universe actually formed by acquisitions and mergers over cosmic time. And so there's a rather more complex history of galaxies than the simple division between spirals and ellipticals would suggest.
Thank you very much, Chris. The next question is from one of our live viewers, and I think this is a good opportunity to kind of explain the limitations of some of our models. Astrophysics, who is on with us live, says there's something strange about space-time warping. In all illustrations of space-time, it seems to be in a fabric that bends around the mass. But what happens if you're directly underneath that object? Like, what if you're not on the fabric, but underneath it?
Right. Well, it's a good question because astronomers, like other scientists, are sometimes limited to models, and the models are imperfect representations of physical reality. Now, that's one of the powers of physics and astronomy at some level, because the underlying physical laws and relationships that govern the universe are mathematical. And you can work the mathematics without any visualization, without any understanding of geometry or representation in a space that you can see visually. But we're visual learners, humans are, so we need these visual crutches. And curved space-time is a particularly difficult concept because the mathematics of that is tensor theory, which is very complex. It's graduate-level mathematics. And so to make it accessible, people tend to use this, they almost overuse this analogy of a curved sheet, a 2-dimensional surface, like a rubber sheet, where it's intuitively obvious if you put a heavy object in that rubber sheet, it would bend and deform the sheet. And then if you rolled a lighter thing, say the bowling ball was the heavy object and a marble was the lighter object, that marble would take a curved trajectory if it passed near the bowling ball because of the bending of the rubber sheet. And that's pretty much what light does relative to curved space-time when there's a massive object. So it's a good analogy in that sense, but we have to remember the limitation. The limitation is it's purely two-dimensional. So relative to the question, it doesn't mean anything. It's meaningless to consider what's above or below the rubber sheet, because this is a little universe in which the rubber sheet is the universe. You have to imagine being a two-dimensional creature trapped in the rubber sheet itself, in that surface, and all you can do is move in that two dimensions, curved or not, and explore it. Visualizing three-dimensional curved space in 3 dimensions, the space we live in, it's really not possible. And I don't even think, there are some diagrams that try to do it, but it's not really very convincing. So I think if you just don't ask the analogy to do something that it's not equipped to do, then these are useful.
Thank you, Chris. I did post in the chat an animation that kind of shows how space-time curves and is bent in 3 dimensions, so that may be helpful to some people. The next question is from Anuj, who's on with us live. The specific question is, do the gravitational waves created by merging of 2 black holes differ if they're of different masses but the same total mass? Like if 2 5 solar mass black holes merge, or if a 7 and a 3 solar mass black holes merge. But more generally, what is it that affects gravitational waves?
Yeah, that's a very good question. Yes, the signature of a black hole merger does actually depend on the individual masses. So it's not a 3 and a 7 mass black hole merging is not the same signal as a 5 and a 5 or a 6 and a 4. It's a good question. And that's just because the nature of the space-time distortion depends in some parts of the mathematics on the difference, and in some parts on the ratio of the 2 masses. So you definitely get a different outcome if they're 2 equal masses. And that's important because when people at LIGO and these gravity wave detectors are trying to understand what they've seen, they use various filters to match to the data, and they can discriminate between these different merger scenarios. And that's how they can take what is essentially a single waveform for a merger event and say, oh, this was a 21 solar mass black hole merging with a 34 solar mass black hole. And of course, there's an uncertainty or error attached to each one. So that's a good question. And actually, the information you can extract from the gravitational wave signature is quite striking. You can also get an indirect measure of how much energy was lost in the merger, which would have been mass from the black holes converted into pure energy in the form of gravitational waves or space-time ripples. And you can also get an indirect sense of the angular momentum of the system. So as the black holes approached each other and merged, what was their initial angular momentum? So there's quite a lot of information you can get. And most importantly, from the strength of the signal, which goes down linearly with distance in the universe, which is not the same way light does. Light goes down as the inverse square. You can estimate the distance to the merger event. And most of the LIGO events are a long way away, over 1 billion light years away.
Thank you very much. The next question is from Ilsa Martin, who is on with us live. The moon is said to stabilize the Earth's orbit. How so, and what would go wrong otherwise?
Well, the moon stabilizes the Earth's orbit in several ways. The moon and the Earth are in quite a tight connection gravitationally, and we know that because the moon is tidally locked to the Earth and always presents the same face to the Earth. That would not be true if an object like the moon was orbiting 4 or 5 times the distance it is now. Then it would be rotating with its own period and still orbiting the Earth, which has its own period. So the fact that we see the same face of the moon tells us that there's tidal locking, which means a very strong gravitational connection. And what you can just think of gravity, the moon reaching out with almost a hand and holding the Earth more stably than it would be otherwise. One of the things the moon stabilizes is the orbital tilt of the Earth, the axis, 23.5 degrees tilted with respect to vertical from the sun, which is what gives us our seasons. If the moon did not exist, you can certainly ask what the Earth would do, and then other perturbations in the solar system would let the axis of the Earth's spin wander over cosmic time. For instance, Mars currently has about the same orbital tilt, so it has similar type seasons to us, but history and history of the Mars orbit and some measurements on Mars surface itself shows that its orbital tilt has varied from about 25 degrees to 45 degrees. It's wandered, and that's because Mars is not stabilized by a large moon. It has Phobos and Deimos, which are tiny moons. So we see very directly, just by comparing the Mars and the Earth, what effect the moon has on us. And some have argued that the large moon size relative to the Earth was part of the conditions that might have facilitated biology on this planet. And if we didn't have such conditions, we didn't have the moon the way it is, biology might have been harder. The climate might have been very variable and inhospitable to life. This became something called the rare earth hypothesis, which said that property plus a number of others were sort of special to the Earth, and so they might not be replicated on other potentially habitable planets.
All right, the next question is from Marta, who sent an email. Is there a way to measure the axis tilt of an exoplanet at the moment? And how would the presence or absence of seasons influence the evolution of life on an exoplanet?
It's a good question. It's sort of the cutting edge of exoplanet research. There's no direct way to measure the axial tilt the way we might in the solar system by observation, because remember, the way exoplanets are studied is basically by measuring their size or their mass. These are global properties. However, there are now a number of exoplanets that have been where we've used occulting techniques to spatially resolve them, or use eclipsing techniques, to watch the properties that reflected light from the planet as it moves through its orbit. And those have given us indirect indications of sort of zones of clouds, and that indirectly, of course, gives us an orbital tilt. So yes, it's been measured for, I would say, only half a dozen, maybe 10 exoplanets. It's pretty hard to do. That's at the frontier of what we can do. I forget what the second part of the question was, actually.
The question was, how would the presence or absence of seasons affect the evolution of life on exoplanets?
Yeah, so that's almost a separate question. So I'll answer it as a separate question. How do the seasons on a planet, any planet, our planet or an exoplanet, affect the likelihood of life or the nature of the life? We simply don't know, because we have one habitable planet in the universe that we know of, and it's the one we live on. So we can't really do the hypothetical what if until we measure some other exoplanets. The speculation, however, is that some level of seasons or orbital tilt is fine for life and not a problem. Maybe too extreme seasons would be a problem. If we had an axial tilt like Uranus, which is almost 90 degrees, 87 degrees, and Venus, and that planet has 40 years of winter and then 40 years of summer, the deep freeze of winter for so long might kill life. Lakes would freeze solid, shallow bodies of water would freeze solid, and so that would kill life as we know it. So seasons that are too extreme are probably inhospitable for life, even getting started. That seems a fair bet, given that we need liquid water, and you just may remove the chance of liquid water with seasons too extreme. But mild or moderate seasons, yes, almost any orbital tilt between a few degrees and 40 or 50 degrees is probably fine. Remember, for a planet that we think will have life, the seasonal variations in temperature are buffered by the atmosphere. So we're also going to be talking about an atmosphere that's necessary for life, to protect life from UV radiation and cosmic rays. And that same atmosphere acts like a buffering blanket that's modulating the otherwise large temperature range of the planet. That's the reason, for example, on our planet, that if you look at the mean temperature through the year, the peak of the mean high temperatures in a northern hemisphere summer is well after the summer solstice of June 21st. It's 6 or 8 weeks after it, and the mean of the low winter temperatures is 6 or 8 weeks after the winter solstice of December 21st, and that's direct indication of the effect the atmosphere has on climate.
The next question is from Wolf and Bree, who is on with us live. Are there layers of toxic gas under the crust of some exoplanets, or under the Earth for that matter?
Very well could be. For the Earth, it's easier to say for the Earth because we've explored the Earth. Yes, there are there are large methane-producing situations on the Earth. Some of these occur geologically and naturally, but there are also methanogens, which are methane-producing bacteria. In fact, the early forms of life on the Earth were methanogens, or methane metabolizing bacteria. Methane in large quantities is a toxic gas. It's a greenhouse gas as well. It's a 20 times per molecule more potent greenhouse gas than carbon dioxide. So it's actually a big component of the global climate change issue. But that's the most common toxic gas produced by life and also by natural geology. Not many other toxic gases. Of course, carbon monoxide, a relative of carbon dioxide. Carbon dioxide is toxic, of course, to humans and other animals in large quantities. But carbon monoxide also exists, a cousin of carbon dioxide, relatively abundant. That's clearly a toxic gas. Nitrous oxide is another example of a toxic gas. We know it as laughing gas, but in significant quantities, it's toxic. So yes, the Earth generates 5, 6, or 7 molecules in significant numbers under the surface that will be toxic to us in large quantity. As for exoplanets, we simply don't know. We have too little information. The experiments to try and sniff out the atmospheres, we don't know about their surfaces or subsurfaces, but the atmospheres of exoplanets have found oxygen, ozone, water vapor, nitrogen, some of the standard things, and carbon dioxide, of course. So we haven't seen any particular toxic gases in exoplanets, but there's very little data yet.
Thank you. The next question is from Saiji, who's on with us live. Could you explain what zero-point energy is and the difference between zero-point energy and dark energy?
Yes, zero-point energy is a concept out of physics, and it actually comes from quantum theory. It says that in the vacuum, the vacuum state does not actually correspond to zero energy, absolutely no energy. The quantum state in quantum theory of the ground energy state of the vacuum is about a Planck constant divided by a half. So there is a finite amount of energy in the vacuum, and that's the zero energy state. As you say, very little different from zero because the Planck constant is an incredibly small number in metric units. What does that mean in practice? It means that the vacuum is a place in which things can happen. And we know that particle-antiparticle pairs can come in and out of existence in the vacuum. That was demonstrated in physics labs half a century ago. So we know the vacuum is a place where stuff can happen. Energy can be created spontaneously for a short period of time, or particle-antiparticle pairs can come in and out of existence. However, it's not the same as dark energy. Dark energy is a quality of the vacuum that appears somewhat similar, but it has a quite different outcome. Instead of creating particles and antiparticles, it causes space-time to expand at an accelerating rate. So it acts as a negative pressure in physics terms, in terms of its equation of state. So that's a really quite different thing from zero energy.
All right, the next question is from Ranjan, who's on with us live. Neutron stars have gravitational accelerations in the 10 to the 11th meters per second range. If you drop an object close to its surface and observe the velocity for a second, won't it be larger than the speed of light?
An interesting question. So yes, neutron stars are obviously just one step above black holes in terms of their gravitational field, their density, their surface acceleration, if you like, because neutron stars do have surfaces. So if you, in principle, and they're also always spinning and often spinning very fast, the most rapid pulsars, which we know are spinning neutron stars, can spin 1,000 times a second, millisecond pulsars. So what would happen if you dropped an object near the surface of a neutron star? It would obey the gravitational acceleration appropriate to the mass and radius of that object. It would not, however, accelerate to faster than the speed of light, because that's not possible for any object. As it approaches the speed of light from a starting point, and accelerates very quickly, because the little gravitational constant g on a neutron star is much higher than it is on Earth, 9.8 meters per second. Yes, would accelerate very quickly, but as it approached the speed of light, heading towards the surface, special relativity says that its mass would increase, and that's an increase in its inertial mass that would resist a change in its motion. So in a very bizarre way that we've never been able to, of course, demonstrate in the lab or even really prove happens, an object dropped towards a neutron star would indeed accelerate rapidly towards the speed of light, but as it did so, would gain mass dramatically due to special relativity and thereby never reach the speed of light.
All right, thank you very much. The next question is from WS, who's on with us live. Why don't we currently see signs of abiogenesis, like protocells and prebiotic conditions on Earth today?
That's an interesting question. So if we think life started from inert chemicals, which we do, and we know a fair amount of the way in which that happened, and we think this happened for the first time about 4 billion years ago. Hard evidence for life only gets back to 3.7 or 3.8, but those are already fairly complex metabolizing organisms, and so the very genesis of life could have been 4 billion or even earlier. So the question is, well, if it happened then, and we're all descendants of that first origination, sort of the last common ancestor, as it's called, could such a thing be happening on the Earth now? And the answer is that aspects of it are happening on the Earth now. We can find aqueous environments, for example, near hydrothermal vents, or in shallow pools in temperate climates, in equatorial climates, where natural evaporation or just the free energy in the atmosphere and the water are enabling chemicals to get together and become more complex. And so in natural situations, we've indeed seen lipids, which are just fats essentially, form natural vesicles, which are sort of protocells. That's the way we think it happened on the early Earth. And we can see those little fatty spheres form in these molecularly dense liquid environments where the water as a solvent has dissolved a lot of chemicals and they got concentrated. So yes, in a sense, we can find particular environments on the Earth where some of the phases that we think went between simple molecules and the first cell happened. But of course, this process took, we don't know how long on Earth. It may have taken tens or even 100 million years for it fully to happen. And so we've never found a place on the Earth where the whole sequence of events is laid out for us. We can also do it a different way. We can look through biological methods and genetic methods for the most primitive or simple cells that exist on the present day Earth. But even those simple cells, the ones with the least genes or the least amount of genetic material, they're still vastly more complicated than non-living matter. So unfortunately, we can't watch the whole process of the formation of life, even in segments of that process, of that chain of events on the Earth.
Excellent. The next question is from Marnouche, who's on with us live. Is there any dark matter in black holes?
That's a good question. So black holes are dark matter by definition. They're dark and they're highly dense matter. So if we think about dark matter in the universe, a dark matter is an omnipresent component of the universe amounting to 6 times the normal matter. And we can ask, what might have happened to, and so we assume that in a place where a black hole forms because a dead star dies, let's just take a single isolated massive star that dies, well, that star will be in a galaxy, and that galaxy will be permeated with dark matter. That dark matter won't be highly concentrated or clustered. It will show a general concentration that follows the mass of the galaxy, but doesn't follow the mass of individual stars. So you can think of a star near the end of its life as sort of existing or superimposed on a low density ambient sea of dark matter. But I emphasize low density because on average, the density of space is very low. So when that star collapses and forms a black hole, it's formed something incredibly dense with an incredible number of now invisible normal atoms that went into it. The dark matter that might have been there will indeed be contained by the black hole as well, but it'll be a much, much lower percentage of that black hole's mass than the normal stuff. Now, I'm sure you can hear that drilling.
Yes, it's coming through, but we're going to power on. Thank you very much for the answer to that question.
Well, let me just ask, is the audio going to be usable? Because I don't want it to be unusable.
Yes, I think, and everybody on with us can still hear you. I mean, it's low and quiet, and I mean, it's quiet in the background. Your voice is much louder than it.
Okay.
So it's still discernible. The next question is from CMTRO, who's on with us live. And the question is, how do you get a clean image of a galaxy that is deformed due to gravitational lensing?
Well, that's a good question. You actually can deconvolve it. You can, because the gravitational lensing event is like a little optical experiment, you have a model. As soon as you see the lensed image, you know how that image has been distorted. So you can do the ray tracing backwards. You basically have to understand what the lensing object is, and when you know what the mass and the radial mass distribution of the lensing object is, you've essentially got a model of the lens. If it was an optical lens situation, it's just like you have a model for the lens. And with a model for the lens, you can take any image and run it back to the object plane, and so deproject what the object was. So that's a pretty reliable method, and so we really can reconstruct what the unaltered, unlensed galaxy looks like in every case.
All right. The next question is from Julie, who's on with us live. Why are most celestial objects that form over time, like planets, satellites, and stars, spherical in shape?
Well, the real answer in physics is its minimum energy quantity and a minimum energy criterion. So gravity obviously operates in all directions through space. And if you have a situation which is initially symmetric, and you have some perturbation, some little alteration that changes the density in some part of that distribution, then that increased density in some like patch of a big gas cloud will make the gravity a little higher in that region. Because gravity acts in all directions, it will exert stronger gravity on the surrounding regions in every direction, and that's a spherically symmetric situation. So it'll start to pull atoms or molecules in from all directions equally. And if you just play that forward, you obviously end up forming a spherical object, because you started with a situation where the gravity force that causes the object to form is a completely symmetric force operating in all directions. So it's a natural consequence of how gravity works.
Excellent. All right, the next question is from William, who sent an email and is on with us live. Do we think that all the gold in the universe or on Earth comes from neutron stars, or does some come from supernova also? So generally, where does all the gold in the universe and in the Earth's crust come from?
So when we talk about where gold comes from, we're really also talking about where various other heavy elements, and if we want to make the analogy to things that humans tend to care about, shiny metals, valuable precious metals, the origin of gold and silver and platinum and all similar metals with similar parts of the periodic table are similar, but let's just call it gold and understand that we're talking about the others too. They do come from a set of different sources, and the neutron star mergers and the advent of multi-wavelength, multimodal astronomy using gravity waves and electromagnetic radiation, multi-messenger is actually the word I was looking for, that's illuminated us on the creation of heavy elements in neutron star collisions and mergers. And it's elevated what we thought was the fraction of these precious metals like gold that are created in neutron star collisions. Now, the paper, this is an active research area, so the hard final number is not known really. We probably don't have enough data on neutron star mergers to know it, but it's the numbers I've read say that about 1/3 to 40% of all the heavy elements, the metals like gold, come from neutron star mergers, and most of the rest come from supernovae. There is a third source, which is neutron capture. So these two first events, neutron star merger and supernovae, are called R process heavy element creations, R meaning rapid. But we've always known that there was an S process that occurs in the envelopes, the cool envelopes of giant stars, where neutrons insert themselves into heavy atomic nuclei and just gradually bump them up the periodic table. And that sequential process of bumping up elements by neutron capture can create heavy elements like gold, not as efficiently, but just as effectively as the R process. And so that's where the last piece of the gold pie comes from.
Okay, the next question is from Lin Chen, who's on with us live. how does the planet, how do planets orbit double stars? If the planets are in a double star system instead of a single star system like ours.
Right. So there are really two regimes for planets in double star systems, and it depends on the nature of the double star orbit. So let's just imagine that planets form in the range of distances from their stars that the Earth and the other planets do from the sun. So that's between half an AU or a third of an AU and 40 or 50 astronomical units. Let's just say that's where planets tend to form, around stars of any kind. And binary stars, we recognize, could have formed together, and their formation process might well have affected the likelihood they get planets at all. But binary stars also can form by capture. In that case, the planet systems around them will be captured too. So you can see there's some complicated scenarios involved, because we don't always know what the history of the binary star was that got it to be a binary. But then there are two regimes, because we know of wide binaries. There are a lot of binaries that we see in the universe that are wide binaries. These are the kind you can see by naked eye or with a small telescope, because they're visual binaries, which means on the sky you see the two stars separated. Now that means in space they're very well separated. So wide binaries with orbits around each other of dozens or hundreds or thousands of years, they orbit each other so widely that the planet systems around them, snugged in at 1 to 50 astronomical units, are essentially unaffected by the companion. So for wide binaries, the planet systems could exist around each star and not even know about the other star. They would not see it at all. At the other extreme, there are some binary stars that are in very tight orbits, very close orbits, where their orbital times are hours or even 90 minutes. I've seen some that are close to an hour, which is incredible. And of course, in that case, if the planets survived whatever process gave the binary in the first place, you could easily have planets at the normal distances of the Earth and Mars and Jupiter and Saturn that, again, were not sensitive to the fact that there's a binary star, because the binary stars are so close to each other that they don't impact the planet orbits. Obviously, there's a middle regime between these two, where the binary stars are moving around each other with distances of tens of astronomical units, up to 100 or a few hundred astronomical units. And that's just the scale where planets would exist. And such a binary system, the orbits would, for absolute sure, with 100% certainty, because people have simulated it, kick all the planets out of the system. So those double stars would have no planets around them.
All right. The next question is from Lawrence, who's on with us live, who would like to know, is it reasonable to say that our universe is an anomaly, since the matter-antimatter symmetry violates some of the general rules of particle physics?
It's not clear that you can say our universe is an anomaly. That's a good question, though, because one of the dominant features of our universe, which is otherwise the same at every location in space and at every direction of space, that's isotropy and homogeneity, shows this really strong asymmetry in terms of matter dominating over antimatter. And we think that asymmetry dates back to the very early universe itself, and when the forces of nature were eventually unified at extremely high temperature and pressure and density. So the universe has very subtle asymmetry built into it. The initial asymmetry in the forces that leads to the gross asymmetry between matter and antimatter doesn't have to be much of an asymmetry at all. It can be 1 part in a billion, say. But it's also true that physics has asymmetry built into it. So it used to be an axiom of particle physics that if you had particle interactions of any kind, they would have certain symmetries. And the global symmetry that always seemed to be obeyed was the joint symmetry between charge. You invert the charge and you see the same reaction. Parity, you invert the spin and you see the same reaction. Or time, you invert the time sequence of the interaction and it's valid in either time sequence. But we've known for 50 or 60 years that there are subtle nuclear reactions that do not conserve the combination of charge and parity. So that's a violation of fundamental symmetry of nature in just physics, nothing to do with the universe or astronomy. Also in the news in the last few months has been a slight asymmetry that's been seen between the behavior of different neutrino species and also between neutrinos and antineutrinos. So we've seen hints of profound but subtle asymmetry in particle properties as well as the universe itself.
All right, we have two sort of related questions. So I'll start off with the first one from Cristiano, who would like to know, how is it that the universe can be 46 billion light years across if it's only 13 billion years old? Does that mean that it expanded faster than the speed of light?
Exactly. Very good. You've answered your own question. Indeed, the model, remember, this is based on a model. This is not direct observation. When we want to measure the age of the universe directly, we have to do things like measuring the age of the oldest stars by their properties, or use nucleocosmochronology, which is the method of looking for radioactive isotopes and inferring how long ago they formed. So we have two more direct measures of the age of the universe, but they do agree with the model of the Big Bang, and they say 13.8 billion years is the age of the universe. Now, if you play out the expansion history of the universe, accommodating our measurements of dark matter and dark energy, you indeed would say that the edge of the observable universe is not what you would naively expect, 13.8 billion light years in any direction, but 3 times that number. And the answer is indeed, because in the first third of the universe's history, before dark matter exerted a decelerating effect, and long before dark energy started it to accelerate again, any 2 points in space-time were moving apart faster than the speed of light. So for some significant fraction of the universe's history, space-time was expanding superluminally, as a physicist would say, or faster than light. And that's how, in 13.8 billion years, you can have regions of space that are 3 times further away in terms of the number of light years.
All right, thank you very much. The next question that's related is, knowing how big the universe is, how is it that we have been able to take pictures of galaxies that are 13 billion light years away, since that's almost the same time from the Big Bang? How is it that that light has gotten to us when it would need, a lot, it seems like it would need older than the age of the universe?
Well, when we say we take a picture of a galaxy and it's 13 billion light years away, remember, we are using a model. We're not age dating that galaxy and saying it's 0.8 billion years old and the Big Bang was 13.8 billion years ago, so it's 13 billion years from behind us. No, this is based on a model of how redshift converts into distance and look-back time. So what you really observe with a galaxy is not its age at all. You observe its redshift. That's the observable quantity, how much its spectrum is shifted to the red by the expansion of space-time. And in a cosmological model like the Big Bang, you can convert simply one-to-one redshift into distance and distance into look-back time. So that's the process by which we infer the age. And so the highest redshift of galaxies we found are about 10, which means their light has been stretched by a factor of 10 since it was emitted, and we observe it now, which means optical light is turned into infrared light, basically. And that's how you get 13 billion years. Your model says the universe is 13.8 billion years old. So this is a galaxy whose light you are seeing when it was in the first 10% of the age of the universe, and that galaxy cannot be more than about 500 million years old, given that it takes a while for a galaxy to form.
Excellent. The next question is from Brendan, who is on with us live. If Earth was orbiting a star that is orbiting the Sagittarius A star in the center of the galaxy, would it always be daytime due to it being in the galactic center and surrounded by many suns? And then even beyond that, what would a planet be like orbiting one of those stars near the galactic center?
That's an interesting hypothetical. Astronomers like to play this game. What would life be like? What would the Earth be like? What would astronomy be like if we lived somewhere else in the galaxy? On an Earth-like planet orbiting a sun-like star, so we don't change the overall. That's really loud. Let me rewind that. What would the sky look like? What would astronomy be like if the Earth was orbiting a sun-like star, but not at our location in the outer suburbs of the Milky Way? So the key distinction is that the center of our galaxy is an extremely high-density stellar environment. The average density of stars in the neighborhood of the sun is about 1 star per cubic parsec. A parsec is about 3 light years. So in an average cube of 27 cubic light years, there's 1 star. That's moderate density. The average distance to the nearest star is a few light years, as we know. In the center of our galaxy, the stellar densities are thousands to tens of thousands of times higher. That's an extraordinary difference. And that means if we were in that location, it wouldn't necessarily change the properties of the sun or the Earth, because the distance between stars, even at those large stellar densities, is still way larger than the distance between a star and its attendant planets. Those relative scales are factors of millions. So a very high stellar density would mean we were in a very bright environment. So basically optical astronomy would be impossible. Infrared astronomy would even be very hard because there's a lot of dust and gas near the center of our galaxy. And even radio astronomy would be difficult because a lot of plasma heated up by not the black hole itself, but by the rapid stellar motions in the center of our galaxy. So unfortunately, the first thing we could say is that astronomy, as we understand it, research astronomy, would be impossible. And optical astronomy, visual astronomy wouldn't be very useful either, because the night sky would be blazing bright. It wouldn't be fully dark. The best guess is that near the center of the galaxy, the darkest it would ever get, assuming we had a moon, is that the whole sky would be lit up the way a full moon illuminates the sky. So you wouldn't even see many stars in the night sky. So it'd be kind of disappointing place in that sense. It would also be a hazardous place because with densities 10,000 times higher than the local neighborhood, the incidence of stellar collisions and interactions is 10,000 times higher. And that means things that might happen on the Earth every few 100 million years might actually happen every 10 or 100,000 years. And some of those could be life-threatening or life-destroying. So this is probably a pretty hazardous environment for life.
All right, the next question from Jose, who's on with us live. He would like to know, how is it that we measure the speed of light? What is the best way to measure it to get the most accurate value?
It used to be a difficult thing to do. The first speed of light measurement that we know of was Galileo going with a colleague to 2 hilltops outside of Padua, and he had a lantern that he could close the shutter on, and his colleague did too. And they arranged that at a prearranged signal, Galileo would let the light from his lantern go to the other hilltop, and as soon as he saw it, his colleague would open his lantern, and Galileo would time the back and forth signal with his pulse. Well, we know that at the speed of light, going so fast, that was an impossible experiment. It was going to take a tiny fraction of a second. That was the first speed of light experiment. The first actual measurement was done by Romer, an astronomer in the 17th century, very clever experiment, using the difference in the time it took light to reach us from one of Jupiter's moons when it was on the near side and the far side of Jupiter from us. So the extra distance across Jupiter led to a time delay in the light from this moon as it's eclipsed by Jupiter. It's a very clever experiment. It only gets you the speed of light to 10%, but that was the first real measurement. And then various electromechanical methods were used up until the mid to late 20th century. So if we just jump forward to the present day, the speed of light is known very, very precisely with a precision of thousandths of a percent, maybe 10 thousandths of a percent. And now it's very trivial to measure the speed of light because we can use optical switches. So electronic light switches can be designed that have a precision of 1 part in 10 to the 15. And that means you can time the movement of light across a distance of about 1 meter or 10 centimeters easily and with high precision. So the speed of light has been measured exquisitely accurately using modern light switching electronics.
All right, the next question is from Aisha, who sent an email. And we talk a lot about things like the Planck limit or Planck constant, Planck mass, Planck time. What are those things? What is the Planck limit or constant?
So this set of Planck numbers that are related to each other in dimensional terms, just based on the units, essentially represents the veil of ignorance about us and the universe. So as you trace time backwards towards the Big Bang, you reach a time called the Planck time, which corresponds essentially to the distance that light can travel corresponding to the size of the smallest subatomic particle. So that's the smallest possible time increment you can imagine. And below that, you can't imagine a time increment. And that number in time units is 10 to the minus 43 seconds. So that is considered the Planck time. The Planck scale is the distance that light can travel in 10 to the minus 43 seconds. So that's an incredibly small distance. And that happens to correspond to the scale at which strings, if strings are actually real entities, that they exist. You can use dimensional analysis to also calculate a Planck mass, and that's a very small microscopic mass, but bigger than a subatomic particle. So there's a set of interrelated quantities, Planck time, Planck mass, Planck scale, that all relate to the very earliest instant of the universe after the Big Bang. These are conditions that we cannot remotely recreate on the Earth. So this is very theoretical, hypothetical work. And because we don't have a quantized theory of gravity that we believe and we trust and we have verified, what happens at the Planck scale, as it's called, is very uncertain.
All right. The next question is from Badger Kitten, Kite, who's on with us live. How were the rocky cores of Jovian planets inferred from observations of passing exploration spacecraft?
Yeah, good question, because what you see is gas giants. So Jupiter, Saturn, Uranus, and Neptune are just big gas balls. And it turns out that we still don't actually have very accurate measurements of the rocky cores. But the way we know their cores exist, well, we can infer, we predict that the cores exist because we think that the way all the planets formed was by the nucleation and aggregation of rocky material to form rocky planetesimals and then Earth-like objects. In the case of the giant planets, there was more material out there, so they made super Earths, probably 3 to 5 to 10 times the mass of the Earth. And then those rocky cores subsequently accreted gaseous envelopes just of the leftover material from forming the sun, with so hydrogen and a little bit of helium. So that's what theory and simulation say. But the question of, do we know? And the answer is yes. Spacecraft, when they orbit these objects, and we've had spacecraft that have orbited, heavily orbited Jupiter and Saturn and done flybys and passing measurements of Uranus and Neptune, and Pluto, of course. These missions have gravitometers on them, and so they can show how the gravity force changes as they move closer and further from their targets in an elliptical orbit. And that's a very sensitive measurement to inhomogeneities. And so if the planet was just a gas ball the size of the planet we see, it wouldn't nearly explain the gravitometer measurements. So basically we know there must be a dense rocky core at the centers of these giant planets. Now the measurement of the mass of it is, I've seen arguments in the literature within the last few years about people arguing for Jupiter whether it's a 3 times the mass of the Earth or 5, and some people even say more. So these are not very accurate measurements, but it's essentially beyond doubt that there are rocky cores there, even though we can't see them.
Excellent. The next question is from Sanka, who is on with us live. What is a Bose-Einstein condensate, and do they have any relationship to astronomy?
Possibly. So Bose-Einstein condensate. So there are 2 fundamental statistical theorems that relate to how particles, subatomic particles, behave. There are particles that are governed by Fermi-Dirac statistics. So these are famous physicists whose names are given to these, Enrico Fermi and Paul Dirac. So Fermi-Dirac statistics apply to particles of half-integer spin, and best example is an electron. And these statistics say that no 2 subatomic particles can have exactly the same set of quantum properties. And that fact actually creates a pressure inside fermions, or inside a sea of fermions, if you had a sea of electrons or other half integer spin subatomic particles, the fact that they can't exist in the not just in the same location at the same time, but also have this exactly the same charge, spin, and other quantum properties, means that these can't be in superposed states. Bose and Einstein, Bose was an Indian astrophysicist, a contemporary of Einstein actually, and they came up with the statistical distribution of describing particles with integer spin. And so this is a different set of particles. A photon, if you want to consider a photon a particle, which you can, has 0 spin, so it's a boson. And bosons have the ability to be superposed, so they can live in exactly superposed states. And so Bose-Einstein condensate is a material that you create and subject to very low temperature of subatomic particles, and it gets coherent properties where it can actually collapse because it is allowed to have a single coherent state. So this is an extraordinary situation. It can lead to superconductivity. It can lead to all sorts of interesting behaviors. It's like the individual subatomic particles know about each other and form a shared quantum state over a significant distance. It's been very useful in electronics, in research to develop new types of superconductors. It's not obvious, and it led to the award of a Nobel Prize to Carl Wieman some years ago. He subsequently moved into science education, actually. But it's not clear that they exist in nature. We can create them in the lab, in other words, but it's not clear that in astrophysics they really exist, although there's been some speculation.
Excellent. Thank you very much. Our next question is from a live participant, a live viewer, who would like to know, is a black hole strong enough to spaghettify another black hole or neutron star?
Well, black holes, we know about black holes when they encounter each other and merge, because we've seen that happen now. LIGO has modeled that. And so black holes are so contained by their gravity in the event horizon that they can certainly distort each other, but they can't sort of rip each other apart, because that would actually imply that the gravity of one black hole could disrupt another black hole. And that almost by definition is impossible, because the event horizon is a boundary to the rest of the universe. So black holes are sealed off sections of space-time where even when they interact, they can't disrupt each other. But that's not true of neutron stars. So if you have a black hole and a neutron star orbiting or merging or interacting closely, definitely the black hole has, generally for the same mass, will have stronger gravity, and it can indeed disrupt the neutron star. A neutron star is like a giant atomic nucleus, so it's held together by gravity. But it has internal forces and stresses, and absolutely a black hole could disrupt, shatter, tear apart a neutron star, and it would be lovely to know if this happens. And actually that's one of the things LIGO is going to try and do, because LIGO should be seeing not just black hole mergers, but neutron star mergers and neutron star black hole mergers. And in that last category, maybe it will see some of these interesting effects.
Excellent. The next question is also from a live viewer. Why does the rate of Hawking radiation accelerate as a black hole size decreases?
That's a good question. So Hawking radiation, it's an interesting phenomena. It relates to the fact that the temperature of the black hole is inversely proportional to the surface area. The entropy is proportional to the area, that's the disorder contained within the black hole, but the radiation, the Hawking radiation itself, is inversely proportional to the area. And so, and that pretty much explains what happens. As the black hole shrinks, its surface area declines, so its temperature goes up, so its rate of radiation goes up, and what you have is a crescendo. And so it just fizzes away to nothing in a final crescendo as it approaches zero mass.
The next question is from Devaparna, who's on with us live. How do we actually know that the speed of light is the universal speed limit?
Well, we don't. It's a strong assumption, a premise built into physics, this theory of special relativity, was constructed using that as an assumption, but that assumption was based on the Michelson-Morley experiment, which showed that there is no universal medium or ether with respect to which light operates. So that means the speed of light is a quantity that you always measure the same way regardless of your motion. And that has been confirmed amply in the lab. So that's really all we can say, is that as we know it, all the situations we can observe or create experimentally, we observe the speed of light to be a constant. We also assume that that operates over cosmic time, and that's an interesting question as to whether the speed of light or other fundamental constants like Planck constant or the fine structure constant may have changed over cosmic time. There have been occasional claims, but and the experiments are difficult to design, but no one's seen any evidence for that either. For a while, there was a theory called the tired light theory, which actually did have light slowing down as it traveled through cosmic time and space. Those theories have actually been ruled out now, just based on the properties of distant light sources like galaxies. So at the moment, it looks like the assumption, the basis of special relativity, does indeed hold that the speed of light is an absolute across space and across time.
All right, and I think this is going to be our last question for today. The question comes from Pashupati, who sent an email. More than 100 years ago, gravitational waves were hypothetical, and now they've been found. Right now, the tachyon is a hypothetical particle. Do you think in the future we will discover something like that?
It's possible, but the situations are quite different. Gravitational waves were a prediction of general relativity, and general relativity was a theory that got very quickly confirmed in terms of gravitational lensing and the gravitational redshift. So within 10 years of its publication by Einstein, there was good experimental support for general relativity. So the fact that it took quite a lot longer to detect gravitational waves was a problem of experimental design, but in the end, it shouldn't have been surprising that they were detected. By contrast, tachyons, or faster than light particles, which sort of exist in a sort of shadow world relative to regular particles, which when you try to make them go faster, approach the speed of light but never exceed it. It's a hypothetical construct in physics that doesn't sit naturally in any fundamental theory of physics. So it is really very speculative. So in that sense, nobody necessarily expects that as time goes on, the detection of tachyons becomes more likely, because they're not posited from some frontier theory of physics that's been tested and leads us to believe that this prediction should be borne out. So those are good questions. I'm actually going to ask the last question of myself, because I think it came up, but maybe not, in a few weeks ago. So I'll ask a question, which is, what is the effect of the coronavirus, of worldwide pandemic, on astronomy, on research astronomy in particular? I know what it is on my department, because they're ripping up the building right now, but most of the people are not coming into work. Social distancing is in operation. But the coronavirus has had a huge impact on research in the United States and worldwide. It's obviously made it very difficult for labs to operate of any kind, because people can't be in their labs in large numbers and work in close quarters, which is what happens in every biology or chemistry lab I've ever been to. It also affects astronomy because although astronomers don't have wet labs like biologists and chemists, we in our department have a lot of instrumentation labs where we're making the next set of instruments or the next set of mirrors for large telescopes. And those labs are very similar places where a lot of engineers and technicians and scientists have to work closely together to do engineering or to make things or to test things. And so being unable to do that is a real limitation. So all the major labs in astronomy on my campus, like the Mirror Lab place where we make our big mirrors, are closed down. And every major observatory that I know of is closed down. There's a website that actually has all the observatories in the world, and they're not all closed, because some are robotic and some are operated by one or two people and they just keep going. But the major observatories, all the major Chilean observatories at Las Campanas, at La Silla, at Pachón, are closed. All the major observatories in Mauna Kea and Hawaii are closed. The major observatories in La Palma that are run by the Europeans are closed. So it's a huge impact on observational astronomy, and it's just frustrating here because you may or may not know where you live, but the skies in Arizona in the spring and the late spring are extremely nice. We've had cloudless night after cloudless night, so my colleagues are getting pretty frustrated. I don't want to end on a note of frustration, so this will pass, I'm sure. Meanwhile, thank you for your questions and look forward to seeing you next week.